Welcome to section 6.3, Determinants. In this section, we look at another algebraic approach for solving systems of linear equations called Cramer's rule. This method is based on determinants, and it can only be used if the number of equations equals the number of variables. Typically, this method is used for systems involving 2 or 3 variables. So objective 1, evaluate a 2 by 2 determinants. So if A, B, C, and D are 4 real numbers, the symbol D equals the determinant AB, CD, and is called a 2 by 2 determinant. Its value is the number AD minus BC. That is, D equals the determinant AB, CD, which equals A times D minus B times C. Caution, the notation for a determinant looks much like a matrix. However, the matrix uses brackets, and the vertical bars are used to indicate a determinant. So that's the difference between a matrix and a determinant. The following illustration may be helpful for remembering the value of a 2 by 2 determinant. So we have our vertical bars here. We have A, B, C, D for the 4 different values. And so to find the determinant, we are going to multiply A times D minus B times C. Okay, so let's evaluate this determinant in our first example. Okay, so we are going to multiply A times B and subtract B times C. Okay, so this will equal negative 2 times 4 minus negative 1 times 5, which equals negative 8 plus 10, which equals 2. So the value of this 2 by 2 determinant is 2. Objective 2. Use Cramer's rule to solve a system of 2 equations containing 2 variables. So solving the system of linear equations by elimination leads to a general result for solving a system of 2 linear equations that involves 2 by 2 determinants. This result is Cramer's rule. So Cramer's rule states that the solution to the system of equations is given by x equals the determinant S, B, T, D divided by the determinant AB, CD. Y equals the determinant AS, CT divided by the determinant AB, CD, provided that the denominator, which is the determinant AB, CD, which equals A times D minus B times C, does not equal 0. Notice that the values for x and y both have the denominator D. Okay? They both have the denominator D. In addition, note that the numerator in the solution for x is D with the coefficients of x replaced by the constants on the right side of the equal sign. We can abbreviate this determinant as D subscript x. Similarly, the numerator in the solution for y can be abbreviated D subscript y. So using this new notation, we can now summarize Cramer's rule as follows. The solution to the system of equations is x equals D sub x divided by D, and y equals D sub y divided by D, where D is the determinant A, B, C, D, D sub x is the determinant SBTD, and D subscript y is the determinant ASCT, and D does not equal 0. If the determinant D of the coefficients of the variable equals 0, so that is Cramer's rule cannot be used, then the system either is consistent with dependent equations or is inconsistent. To determine whether the system has no solution or infinitely many solutions, we'll solve the system using previous methods of substitution or elimination. So in our example here, we're asked to use Cramer's rule, if applicable, to solve the system. So in order to use determinants, we have to have the same number of variables to equations. So we have two variables, x and y, and we have two equations. Therefore, we can use the determinant. Okay. So D is going to be equal to the determinant of 2, -4, 5, and 1. Okay, so the coefficients of our variables. So we're then going to multiply 2 times 1, which is A times D, minus 5 times -4, which is B times C. And so that gets us 2 plus 20, which equals 22. Okay. So the x coordinate is going to be subscript d subscript x divided by d. Okay. So the determinant, not discriminant, that's actually something else. But the determinant of x is going to be -8, 13. So your constants replace the coefficients of the variable you're trying to find. So -8, 13, and then -4, 1, divided by 22. So that's going to equal -8 times 1 minus -4 times 13 divided by 22. So that's -8 plus 52 divided by 22. So that's 44 divided by 22, which equals 2. Okay, so the x coordinate is 2. The y coordinate is equal to the determinant of y divided by d, which will be 2, 5, and then -8, 13. Oh, no, need that line there. 13 divided by 22. So we will have 2 times 13 minus -8 times 5 divided by 22, which equals 26 plus 40 divided by 22, which equals 66 divided by 22, which equals 3. So our solution is going to be the ordered pair 2, 3. Excellent. Objective 3. Evaluate a 3 by 3 determinant. So to use Cramer's rule to solve a system of 3 equations, a 3 by 3 determinant is used and is symbolized by the determinant presented here, in which all of the a subscript ij's are real numbers. Okay, so all of the entries within the determinant are real numbers. The double subscript is used to identify an entry by indicating row and column numbers. So the value of a 3 by 3 determinant may be defined in terms of a 2 by 2 determinants by the following formula. So we have our 3 by 3 determinant here, and it will be equal to A subscript 1, 1 times the determinant A subscript 2, 2, A subscript 2, 3, and then A subscript 3, 2, A subscript 3, 3, minus A subscript 1, 2 times the determinant A 2, 1, A 2, 3, A 3, 1, and A 3, 3, plus A subscript 1, 3 times the determinant A 2, 1, A 2, 2, A 3, 1, and A 3, 2. So the 2 by 2 determinants in the formula are called minors. Okay, so all of these are called minors of the 3 by 3 determinant. For our n by n determinant, the minor, capital M subscript ij, of an entry A subscript ij is the n minus n by n minus n determinant that results after removing the ith row and the jth row. Okay? So in other words, we found the determinant by applying the 2 by 2 determinants to the first row. So to find the determinant of our first entry in the first row, we are going to remove the entries in the first row and in the first column. Then our minor will be the remaining entries, which is exactly what we see right here. Okay. If we look at the next entry, okay, so we're going to evaluate using the first row. So if we look at this entry, we will remove the first row and the second column, which then leaves the following entries that make up the second minor. Okay, and then it continues on. So let's now apply this to an example. So we have a determinant here, A, and we're asked to find M subscript 1, 3 and M subscript 3, 2. So let's first find M subscript 1, 3. Okay, so we know our determinant is given here by A, and we want M subscript 1, 3. So we want the minor that is formed with the entry at subscript 1, 3. Okay, so this is the entry that has subscript 1, 3. So row 1, column 3. Okay, so that means we're going to eliminate the first row and the third column. So our minor that's formed is going to be 3, 3, negative 1, 0. Then to evaluate that, we'll get 3 times 0 minus 3 times negative 1, which equals 0 plus 3, which equals 3. Okay, so let's do the next one. So for M subscript 3, 2, we are going to find the minor for the entry at row 3 column 2. This is the entry 0. So that means we're going to eliminate the third row and the second column. So the remaining entries are going to be our minor. So that's 1, 3, -2, -4. So then we will multiply 1 times -4 minus -2 times 3. That gets us -4 plus 6, which equals 2. All right. So next we explore the definition of cofactor, which will help us determine whether to add or subtract each minor when finding a 3x3 or larger determinant. So for an n by n determinant A, the cofactor of entry A subscript ij, denoted by capital A subscript ij, is given by A subscript ij equals -1 to the power I plus j times capital M subscript ij, where Mij is the minor of entry A subscript ij. So to find the value of a determinant, we multiply each entry in any row or column by its cofactor and sum the results. This process is referred to as expanding across a row or column. Okay? So let's break this down. For example, if we're asked to expand this determinant across the first row, okay, across the first row, so this will be the first row, it would result in the following. So remember the first row, we're expanding across the first row. We would have 1 times A subscript 1, 1 times its minor, plus -1 times A subscript 1, 2 times its minor, plus 1 times A subscript 1, 3 times its minor. Okay. If we were to expand across the second row, second column, so that would be this column right here, we would have -1 times A subscript 1, 2 times its minor, plus 1 times A subscript 2, 2 times its minor, plus -1 times A subscript 3, 2 times its minor. So how do we know whether it's a 1 or a -1? We would use the cofactor formula. So for example, we can take, let's take this first one up here. All right, so if we substitute in our I and j into the cofactor formula, we would get -1 to the power 1 plus 1, which equals 1. And that's where we got this 1 from. If we take the next one, -1 to the power 1 plus 2. So this will be 1 squared, which equals 1. There we go. And this will be -1 squared. All right, -1 to the third power, and this would equal -1, which is where we got this -1 from. And then the third, we'd have -1 to the power 1 plus 3, which equals -1 to the fourth, which equals 1, which is where we got this 1 from. Okay, so that's where the cofactors come into play. All right. So if we observe the signs -1 to the power ij associated with the cofactors alternate between positive and negative according to the following pattern. So the first row is 1, -1, 1, -1, and so on. Second row starts at -1, 1, -1, 1, because all you need is the location of your entry, whether it's row 1, column 1, row 2, column 2. which is your I and j, that you're multiplying or adding together as the power of -1. So it can be shown that the value of a determinant does not depend on the choice of row or column used in the expansion. So expanding across a row or column with the greatest number of zeros reduces the amount of work needed to compute a determinant. Okay, so you can expand across any row or any column. Choosing which row or column, I would encourage you to identify the row or column with the lowest value or the one that contains the most zeros. Because if your entry is a 0, that means these values here would be 0, which then eliminates this whole section because anything times 0 is 0. Okay. Another thing to know about the cofactors is if I plus j is even, then we would have -1 to the I plus j will equal 1. Okay? If it's even, if your power is even, then you will always equal 1 for A. If I plus j is odd, so like 3, 5, 7, and so on. So if A here equals -1, then you know you'll be multiplying your entry and its minor by the cofactor -1. Okay, so that's just an easy little trick to help you when you're expanding. If the entry row and column summed is even, then you know it's a 1. If the row and column is odd, the sum is odd, then you know it's -1. Okay. So let's evaluate this 3x3 determinant. Okay. So again, we can expand across a row or a column, whichever one. I am going to choose row 2 to expand across because row 2 has a 0, thus making it easier to expand. So let's expand across this row. All right. So I'm going to have, since this is row 2, so I'm going to start with the first one here. Row 2, column 1, so 2 plus 1 is 3. I'm going to start with a -1. So I'll have -1 times 0 times the minor that's formed at this entry. So I'll eliminate the first column as well as the row, which will leave me with -1, 3, 1, and 2. Okay. Then I will take the next entry. So I will then add 1 times 3, whose minor is going to be 2, -5, 3, and 2. Then I will add a -1 times 4, whose minor is 2, -5, -1, and 1. Okay. So now we can simplify. So this first entry here, this first term is being multiplied by 0. So we know this is going to equal 0, this whole entry here. Okay. The next one, we are going to add 3 times the determinant, which will be 2 times 2, which is 4, minus 3 times -5, which is -15. Okay. Plus, then we have -4 times the determinant. So 2 times 1 is 2, minus negative 5 times negative 1, which is 5. We can simplify some more. So 3 times 4 minus a negative 15 is going to be 19, plus negative 4 times 2 minus 5, which is negative 3. So 3 times 19 is 57. And then we have plus 12, which equals 69. Okay. So the value of this determinant is 69. All right. Objective 4. We are going to use Cramer's rule to solve a system of 3 equations containing 3 variables. So we're going to consider first the following system of 3 equations. Note that we have 3 variables and we have 3 equations. It's a requirement for Cramer's rule. It can be shown that the system has a unique solution if the coefficients of the, I should say variables, is not 0. That is, if the determinant does not equal 0. The system then has a unique solution. The solution can be found using Cramer's rule. So our theorem here states that if the determinant does not equal 0, the solution to the system of equations is going to be given by x equals d subscript x divided by d, y equals d subscript y divided by d, and z equals d subscript z divided by d, where we have the 3 determinants for d subscript x, d subscript y, and d subscript z. Okay? All right, so now let's apply this to an actual example. So we're going to use Cramer's rule here, if applicable, to solve our system. Okay? So the first thing that we need to do is make sure that we have the same number of equations as variables. So in this example, we have 3 equations labeled 1, 2, and 3, and each equation has 3 variables, x, y, and z. Okay, so that matches, so we know we can move forward. So now the next thing is to find our determinant, d. So we're going to take the coefficients of all of our variables and place them within our vertical bars. So we have 1, 2, negative 1, 1, negative 3, negative 2, negative 1, 1, and 3. Okay. Now I want to choose a row or column to expand this determinant to find its value because it's 3 by 3. So the row or column that I'm going to use to find my value for the determinant is going to be row 1. And I've chosen row 1 because it all has 1s or negative 1s, which will be much simpler to multiply. Not saying 2 or 3 won't be simple, but more simpler. Okay, so let's expand. So I'm going to first take my entry 1. That's in row 1, column 1. So 1 plus 1 is 2, so that's even. So I'm going to be multiplying by 1. Then I'm going to take my entry, which is 1, times my minor, which will be negative 3, 1, negative 2, and 3. Then I will add negative 1 times the entry, which is 1, times its minor, which will be 2, negative 1, 1, and 3. Then I'll add negative 1 times its entry, which is also negative 1, times its minor, which is 2, negative 3, negative 1, negative 2. Then I can simplify. So I'll have 1 times the value of my 2 by 2 determinant, which would be -9 minus -2, so I multiplied across, plus -1 times 6 minus -1, plus -1 times -4 minus 3. Simplifying some more, I'll have 1 times -7 plus -1 times 7 plus -1 times -7, which equals -7 minus 7 plus 7, which equals -7. So the determinant D equals -7. Okay? So now let's find the determinant D subscript X. So that means for the column that represents the coefficients of the X variable, I'm going to replace those values with the constant. So now I will have 1, -15, and -3. And then the coefficients of Y and Z will remain the same. So 1, -3, -2, -1, 1, and 3. Okay. So similarly to how we found the value for the determinant, we are going to do the same thing for the determinant of subscript X. So we want to choose a row or column to expand this by. I am going to stick with my row 1 because they all contain 1s. Okay, so I'll start off with 1 times my entry, 1 times the minor, which is -3, -2, 1, and 3, plus -1 times the entry 1 times its minor, -15, -3, 1, and 3, plus 1 times its entry -1 times its minor, -15, -3, -3, -2. Okay. Now my first term here is exactly the same term that I got when finding the determinant D. So I already know what that value is going to equal, which is -7. So now I can evaluate my other two terms. So I'll have plus -1 times -15 times 3, which is -45, -3 times 1, which is -3, plus -1 times my determinant, which is -15 times -2, which is 30, minus -3 times -3, which is 9. Okay, so I'll have -7 plus -1 times, and I add 3, so -42, plus -1 times 30 minus 9, which is 21. Okay, so I'll have -7 plus 42 minus 21, which will equal 14. Alrighty. Excellent. Now let's find D subscript Y. So we're going to do the same similar process that we did with D subscript X. where we're going to change the coefficients for the y variable to the constants, and we'll keep the coefficients for the x and the z variable the same. So the x is the same, so that's 1, 2, negative 1. These will be the constants, 1, 15, negative 15, and negative 3. Then we'll have negative 1, 1, and 3. And I'm going to expand across the first row like I did before. Okay, so starting off with 1 times the entry times its minor, negative 15, negative 3, 1, and 3, plus negative 1 times its entry, 1 times its minor, 2, negative 1, 1, 3, plus 1 times negative 1 times its minor, 2, negative 15, negative 1, and negative 3. Okay. Now, in this case, our second term here is similar to the second term that we found when we evaluated for the determinant D. And we know that that equals negative 7, as we got right here. So this term right here is the same. So we know that value equals negative 7, so we can already state this when we are simplifying as negative 7. So we have 1 times negative 45 minus negative 3 plus, we already know this to be negative 7, plus negative 1 times negative 6 minus 15. Okay. So then this will equal 1 times, so it's plus 3, so minus 42, plus negative 7, plus negative 1 times negative 21. So this will equal negative 42 minus 7 plus 21, which will equal negative 28. Awesome. Okay. Last one is the determinant subscript z. So similar process. The coefficients for the variable z, we're going to replace with the constants, and we will keep the coefficients for the x and the y variable the same. So that's 1, 2, negative 1, 1, negative 3, negative 2, negative 1, 1, 3. I'm going to continue to expand across the first row. So starting with 1 times the entry 1 times its minor, which is negative 3, negative 2. Ooh, I forgot to change the coefficients for z. Ooh, good catch. So 1, 15, negative 3. There we go. Now we can continue. All right. So negative 3, negative 2, 15, and negative 3. Awesome. Plus, this will be negative 1 times my entry, which is 1, times its minor, which is 2, negative 1, 15, and negative 3, plus 1 times 1 times its entry, which is 2, negative 1, negative 3, negative 2. Okay. All right. So here we have 1 times 9 minus negative 30 plus negative 1 times negative 6 minus negative 15 plus 1 times negative 4 minus 3. So we will get negative 21 plus negative 16 plus, sorry, not negative 16, negative, oh, this should be negative 5, wait, yeah, all of this should be negative 15. Ooh, let's fix that. I just noticed that I didn't put a negative in front of my 15. Negative 15. Yeah, so all of those should be negative 15. All right, let's fix this. So negative 15 times negative 2 is a positive 30. Negative 15 times negative 1 is a positive 15. Okay. All right, so 9 minus 30 is going to be a negative 20. Oh, so I did write that one right. Oh boy. Okay, and that's being multiplied by 1. Then we have negative 1 times, this will be negative 21. And then we have 1 times 7, negative 7. So we have negative 21 plus 21 minus 7, which will equal minus 7. Excellent. All right. So from our expanding, we had d equals negative 7. We had d subscript x equals 14. We had d subscript y equals negative 28. And we had d subscript z equals negative 7. Therefore, x equals 14 divided by 7, which equals negative 2. Y equals negative 28 divided by negative 7, which equals 4. And z equals negative 7 divided by negative 7, which equals 1. So our solution is the order triple, negative 2, 4, and 1. So this is the solution to our system. All right. That was a lot of fun. I love algebra. All right. So as before, Cramer's rule cannot be used when the determinant of the coefficient is 0. So if d equals 0 and at least one of the determinants, d subscript x or y or z, is different from 0, then the system is inconsistent and the solution set is null. If d equals 0 and all the determinants, d subscript x or y or z equals 0, sorry, not or, and, so all the determinants, so d subscript x, y, and z equals 0, then the system is consistent and dependent. So there are infinitely many solutions. The system must be solved using row reduction techniques. Okay, so the first one is or, the second is and. Okay. All right, objective 5, know the properties of determinants. So our first property states that the value of a determinant changes sign if any two rows or any two columns are interchanged. So in our example here, to show this property, we have our determinant 5217, and it's asked us to find it. So let's do that. So we'll have 5 times 7 minus 1 times 2, which equals 35 minus 2, which equals 33. Now for B, it's asking us to swap rows 1 and 2 and then find the determinant. So if we swap rows 1 and 2, we'll have 1 and 7, 5 and 2. So let's evaluate that. So we have 1 times 2 minus 5 times 7, which equals 2 minus 35, which equals negative 33. Okay, note that those values are opposites. Okay, so the value of the determinant changes sign if the two rows are interchanged. Okay. Our next property says that if all entries in a row or any column equals 0, then the value of the determinant is also 0. Okay, so just for an example to have in your notes, say we have 2, 1, 0, 0. If I evaluate this, I'll have 2 times 0 minus 0 times 1, which will equal 0. Same thing if I had zeros along a column, I would have 2 times 0 minus 1 times 0, which equals 0. Okay. Our next property says that if any two rows or any two columns of a determinant have corresponding entries that are equal, the value of the determinant is 0. Okay. So in our example here, we're asked to find the determinant of 214, 214, 325. Note that row 1 and 2 are exactly the same. So let's choose a row to expand upon, and we're just going to use our first row here. Okay. So this would be, since it's row 1, column 1, we are going to start with 1 times our entry 2 times the determinant. It's 1, 2, 4, 5, plus, and this will be negative 1 times our entry 1 times our minor 2, 3, 4, 5, plus 1 times our entry 4 times its minor 2, 3, 1, 2. Okay, so then we'll have 2 times 5 minus 8 plus negative 1 times 10 minus 12 plus 4 times 4 minus 3, which equals 2 times negative 3 plus negative 1 times negative 2 plus 4 times 1. Simplifying, we get negative 6 plus 2 plus 4, which equals 0. Beautiful. So again, if any two rows or if any two columns have the same corresponding entries, then the value of the determinant is 0. So if you ever get that case when you're trying to expand, just note right off the bat, according to this theorem, that the determinant equals 0. All right, our next property. If any row or any column of a determinant is multiplied by a non-zero number k, the value of the determinant is also changed by a factor of k. So let's find a determinant, and then we'll multiply a row by k to find the result. So here we have our determinant 3, 2, 1, 5. So this would be 3 times 5 minus 1 times 2, which equals 15 minus 2, which equals 13. So now let's multiply row 1 by k and find the resulting determinant. So that would be 3k, 2k, 1, 5. So I'll have 3k times 5 minus 2k times 1, which equals 15k minus 2k, which equals 13k. So if any row of our determinant is multiplied by a non-zero, in this case it's k, the value of the determinant is also changed by a factor of k. Okay, so that is the same thing as k times 3, 1, 2, 5. Okay. All right, and our last property here. If the entries of any row or column of a determinant are multiplied by a non-zero number k, the result is the corresponding entries of another row or column. The value of the determinant remains unchanged. Okay, so to prove this property, let's find this determinant and then apply a row operation. So our determinant here is 2, 3, 4, 1. So that would be 2 times 1 minus 3 times 4, which equals 2 minus 12, which equals negative 10. Now we want to multiply row 2 by negative 3 and add to row 1. That is our 1 equals negative 3. Well, the new row 1 equals negative 3 times row 2 plus row 1. Okay. So we're going to start off with our original determinant. Then we're going to apply this row operation and then evaluate. So our row 2 stays the same. So negative 3 times 4 plus 2, negative 10. Negative 3 times 1 plus 3, that's 0. So this will equal negative 10 times 1 minus 4 times 0, which equals negative 10 minus 0, which equals negative 10. Alrighty. And that concludes all of the properties for determinants. And it also concludes section 6.3.